All right, lots to do today as usual, so we will get cracking. Good to see everybody. Hope you have a great week. Nobody shed a tear. This is our second to last live session. Getting to it, getting down to the nitty gritty. So two things I want to do tonight. I'm already recording. Thank you, everybody. Throwing that in there. Two things I want to do tonight. Look at everybody's quiz questions. Please ask a ton of questions. I'm going to go through a bunch of examples, cover some bases, cover some big ideas. And then also, I want to go over the project. So we've got a project for Unit 13 and 14 homework. So we don't have any, you're done with the homeworks, but we do have a project. So I'll assign groups at random, get paired up, and you will have the opportunity to work on this project. A little mini project that actually should send you off nicely into next semester. So it'll actually give you something to put on a resume or something to talk to any data scientist. Kaggle project. So if you haven't done anything with Kaggle, you're going to get used to that website. And I made a little video, so that video is out there. Oh, that's what I did. So there should be, actually I'll take you out there now. So let's go ahead and get started. Great to see everybody. Again, I like the questions always. Last semester was good. Last class. So fire those away, but let me take you out to this project. And I'll hopefully reserve some time at the end to go over it, but we'll definitely go over it. So not even hopefully. We'll make sure to reserve some time at the end. Or maybe we'll just go over it right now. Let's just go over it right now. We are recording, so that is nice. If you go to our website, if you want to follow along with me or just go to Canvas yourself, if you go to Canvas and go to modules, so this is where the thing was last time. So here is, so again, this is I put this out there for the immersion. So when we had the immersion, we had the kind of video lecture here. And these were Chapter 9 videos because I forgot to record last week. So this was should have been a really good synopsis of what we did. This right here is Project Homework 13 and 14, and it's an intro to Kaggle. So I spent a lot of time putting that on there, and you can watch it over and over again. I think it's pretty good. I'm going to take you, so I won't waste too much time just repeating what's in there. But if you go to Kaggle, you just go, I think the video begins like this. Go to Google and just go over to Kaggle, and you'll see the first thing that comes up is this, your home for data science. So if you get in there, you'll need to sign up. So if you don't already have a username and password, I thought I was on a super fast connection, but sometimes you gotta wait. Maybe a bunch of people are trying to get into Kaggle. So this will come up. There's all sorts of image recognition contests, what have you. But if you go to competitions, again, you'll need to sign up with an email. It's totally free to sign up. You go to competitions. This is the competition that we'll be doing, housing prices and advanced regression techniques. So you click on that guy, and it's got an overview. Again, all of this is in the video. It's got an overview. You can come over here to the data, and we've got the training set and the test set. So we're going to go over more of that in the future. But basically, you're trying to use the training set is what you're going to build your model with. So don't even worry about the test set right now. The data set that you're going to try to build a model with is the training set, so train.csv. And in there, actually, I can show that to you real quick. So kind of just doing the video here, but this is good. Please ask any questions as you see it. But what you're trying to do, just so I can get everybody started, there's this really big data set, very interesting data set. Why that happened? Train TV, download the file.
I was just going to let you know, I don't see the module out there yet for this.
Uh-oh.
Yeah, I also don't see it.
I am really bad at Canvas. So you can see my screen, right?
Yeah.
Yeah.
So there's MSDS 6371. That's us. Oh, go to modules. Sorry, are you in modules?
Yeah.
Oh, you got to hit that button. All right, you should see it now. If you refresh.
Yep. Yeah. See.
Yep.
Yep.
It can be published. It's weird. It can be published here, but if it's not published there, then nobody can see it. Vice versa. Okay. So everybody should see that. Again, just going over to Kaggle. What was that? Oh yeah. So I just brought up this data set. So here is your data set. It's a very, I wouldn't say very wide. It's wider. It's the biggest data set we've probably seen yet. It's got 1,460 rows. Each one of these rows is a house. And you can read all about it, read about it with your group, and I can answer questions on Sunday or via email. But it's got a house ID that goes all the way to 1,460. If I can scroll down there right quick. There's the end of it, right there. So 1,460 houses. Those are each an observation. And in those observations, we've got the neighborhood it came from. We've got the lot area. We've got, this is a real data set, and this is really the things you come with. There's some outliers in this data set. There's some missing values in this data set. You're going to have to really spend some time cleaning it up and try to build the best model you can. It's got miscellaneous features. It's got porches. It's got information on pools. So let me say this, though, because I gave this, this is a great data set. Don't get overwhelmed. We're in 6371, and we're just learning multiple linear regression. Do not get caught up trying to build the best model, because remember, all models are wrong and some are useful. There's a way to build a very, very, very useful model, but it's going to take more time than we have. So basically, what I recommend to you is build a very simple model. Start with maybe a simple linear regression model, and so you can start this week building just a very simple model, and kind of building the model that way. Next week we'll learn how to do variable selection techniques. You can read ahead. Obviously, you're going to see the videos on that pretty soon. In fact, there's no homework this week. You can go ahead and start watching those after we get done here. But long story short, there's a ton of explanatory variables in here. I would just forget most of them for now, and start with a simple linear regression model and just answer the questions as you see them. I'll go ahead and bring that up now, though. On Canvas, if you look in files, there's something called like Chapter 13 and 14 project. So if you do this, let's just go there. So if we go here, there is something in here called Files, Chapter 13, Project Homework 13 and 14. So if you go there, you'll see this. This is your training set. I recommend downloading it from from Kaggle, but you can get it here too. This is a cleaned version of the test set. I'll go over that more next time. So now you're just trying to build a model on the training set. Here's the project description. Download. You can look at that. And
is that available right now?
Can anybody see it? It should be.
Yeah, I can see it. I got it. It's out there. It's like in a folder at the top, Max. It's up at the top.
Oh, I got it. Project 13. Yeah, I was looking at the bottom. Yeah. Thank you. Cool. Thank you.
Yep. Project homework 13 and 14. It's a challenging project, but what? But I think you'll have a lot of fun with it, and it's obviously very applicable, very real world, and it should help you in a lot of different ways. AKA, having done a Kaggle project, that's something you can report in the things you'll learn in this will be very handy, and you can talk about it in interviews, you can talk about it in promotion. But anyhow, did I just download that? So here it is. The idea is this. I'll put you in groups at the end of the class. You can get to where I just was by clicking on that link. Your question of interest, though, you've got two analyses that you're trying to do, and you'll have two people. So your team's objective is to conduct two analyses. Assume that Century 21, the data set is in Ames, Iowa, has commissioned you to answer a very important question with respect to their business. Century 21, Ames only sells houses in the Names, Edwards, and this neighborhood called Barkside or Brookside neighborhoods, and would like to simply get an estimate of how the sales price is related to the square footage of the living area of the house. So there's a column in there called GR Live Area, and it depends on which neighborhood the house is located in. Build a model that will answer this question, keeping in mind that realtors prefer to talk about living area in increments of 100 square feet. Provide your client with the estimate or estimates if it varies by neighborhood. So hint, hint, you'll have to, you've got a categorical variable here, you've got a continuous variable here. We went over last week how to handle both of those in the same model, how to fit different intercepts and different slopes, and how to check for that. Turns out Century 21's leadership as somebody who knows statistics, therefore make sure and provide evidence that the model's assumptions are met and that any suspicious observations, outliers, influential observations have been identified and addressed. Finally, of course, provide your client with well-written conclusion that quantifies the relationship, aka confidence intervals, between living area and sale price with respect to these three neighborhoods. Awesome. We're going to cover a lot of how to do that tonight, or some of the pieces you'll need. So that's what I call, we've got two main reasons for regression. One is interpretation. That's what this side is. The next one is what Kaggle's centered around, is prediction. So this one simply build the most predictive model for sales prices of homes in all of Ames, Iowa. This includes all neighborhoods. Your group is limited to only the techniques we've learned in 6371, no random forests or other methods that we haven't covered. Specifically, you should produce 4 models, one from forward selection, one from backwards elimination, one from stepwise selection, and one that you build custom. You can start building your custom one right now, getting used to it, and it should be very easy to add on the variable selection technique when you get there. Generate an adjusted R-squared, we'll cover that tonight, CV press, and Kaggle score for each of these models, and clearly describe which model you feel, and I'll cover what those are next week, you feel is the best in terms of being able to predict future sales of homes in Ames, Iowa. In your paper, please include a table similar to the one below. The group with the lowest public Kaggle score will receive an extra 3 bonus points on the final exam. Nice work. Quick note on Kaggle completion. We only have, what did I say here? We only have one course under our belt so far, but you can, that should be competition. Not competition. How do you spell competition? Competition. We only have one course under our belt. Basically, we're not trying to win a Nobel Prize here for prediction. We're just trying to use some of the things we have. We don't have, some people spend months trying to get this Kaggle score down. We're just trying to build a model, a decent model, and submit it to Kaggle to get a score. The more you get into it, the more you can reduce that Kaggle score. But the Kaggle score is basically, what is it? It is you can check it out right here. I put it in the video. I forgot what the loss function, aka optimization function, is. But if you go out here to overview, to evaluation, the metric, we are trying to reduce the root mean squared error. And I'll go ahead and tell you, it's all in the video, but I'll go ahead and tell you, we're trying to build a model with this guy. Notice that the response variable is sale price. It's way over here on the end. That's the response variable. So we're trying to build a model that will predict sales price. Okay, great. When you look at the test set, when you come over here and you look at this test set, just to give you an idea where we're going, when you look at the test set, notice that the test set has all these same explanatory variables, everything's set here, except there's no sale price. It's not even a column for sale price. You're trying to use these variables, these explanatory variables, to predict the sale price. This is the test set. Who has the sale prices? Kaggle has the sale prices. So you're going to provide predictions, and I'll show you how to get them. It's all in the video, but I can show you office hours, or I'm going to show you next week. But again, it's in the video, how to get the predictions for these and then submit them to Kaggle. Kaggle takes your predictions. Kaggle takes all your predictions and then checks them against it, and looks at the Rubin square error. It takes the observed minus the actual one. I mean the predicted. It's going to take your predicted one, subtract it from the actual one, get that distance, square it, and then do that for all 1,459 of them on here. Whoever has the lowest score of that will be the winner. So in your groups, you're going to have to really kind of digest that and get into it. But I think that's it. So any questions on that? I encourage you to watch the video. That'll probably answer a lot of questions. But that's the main idea. You're going to do an interpretation. You're going to do a prediction. I've got a video out there on how to submit them, and you should be set. Should be really fun. We get started on it earlier than later. Definitely get started trying to clean the variables up. You're going to run into some issues that we'll have to work through, but in the end, that's real data science, and I'll help you through every piece of it. I just got done working with this data set in 3 different classes, so I'm pretty on top of it as to what can go wrong.
Professor, Priyanka is trying to get into the class. She needs your permission.
I just saw it.
Thanks.
Yep, she could be good. Thank you. Okay, so that's that. We've got lots to do tonight, so let's go ahead and get on it. That's the project, and again, I will put you in groups on that tonight. So we'll do that at the very end. So let's go ahead. I'm on the Mac side tonight, so I'm going to share my screen.
Excuse me, Dr. Sadler.
Yes.
I have some emergency, so I have to leave. I won't be able to continue this class.
I'm sorry?
I have to take my kid to the hospital. He's not doing well, so
go.
I won't be able to continue this process.
Yeah.
Okay, thank you.
Yeah.
Harry, good luck with your daughter or son.
Yeah, thanks.
Yeah. So, be sure to send Hari a nice note later. I hope that's not too as serious as it sounded. I'll assume that they'll be all right. So, I guess we'll just go ahead and get started.
Hey, Professor, may I ask a quick question just before you get going? Josh and I weren't able to find any 6372 for the summer. I just want to know if it was only he and I who couldn't get in, or did anybody get into 6372 for the summer? Well, I guess they're not. All right. Thank you.
Why are you not able to get in? There was no.
There was no offering for it. On April 10th, where they went, where they opened up for the summer, there were no sessions. They said that they were already full, and they're going to try to create other sections. But
yeah, there was only 3. There were only 3 available, so 45 spots. And that was it.
Huh. Well, that's
all right. I just want to make sure. Yeah.
So nobody got into 6372?
I got in. I was on it because it's only 10 o'clock here, so I was right on it at 10. But they were going fast.
So has anybody talked to you? Anything? Asking you?
Yeah. I sent out an email saying, hey, we couldn't do it, so we signed up for 2 other classes, and they said that they're going to see if they could open up other sections for the summer, because I would think you'd want to do Stat 2 right after Stat 1, not Stat 1, take a semester off and then start again.
Well, nobody's ever done it the other way, so I don't know if it's better or not or the same. But certainly we'd like to have that option. Let me talk to Daniel this week, and or I'll send you Friday. Yeah, I'll send him a note tomorrow, and I'll figure out if there's going to be one. I imagine you can still change your schedule if that's what you want to do if they open one up.
Yep.
Yeah. Sorry. Yeah. Thanks for bringing that to my attention. Let's rock. I'll put that on my things to do. You guys are the chosen ones. You need to have these options. So let's do it. So here we go. I read everybody's quizzes, the things at the end of the quizzes, so I want to answer all those. Can you see my screen right now? It says Unit 13.
Yes.
Okay, great. So here we go, Unit 13, boom, steps in multiple regression. Of course, we want to plot the data. Here we go. We're starting up the mountain. We want to plot the data. We're going to develop a tentative model. We're going to see lots of examples after this today. Using the questions of interest, we want to have the question of interest. This is what you're going to do in your project. Plot the data first. Look at different plots. Get a feel. Do exploratory analysis. Look at, try to find some outliers. See if there's missing data or there's data that's not appropriately recorded. All of that. Then by your questions of interest, you're going to develop a tentative model. You want to also part of your model, if you want to account for confounders, you want to put those into the model. And also you want to account for relationships. We're going to kind of go over this tonight too. The true relationship between x and y may not be, y equals x. It might be a quadratic. It might bend a little bit. It might be an x cubed. So you might want to add interactions in there. Then you want to fit the model. After you develop the model, we're going to put it into SAS. You get the parameter estimate. That's fitting the model. And we want to look at the residuals. Are the assumptions met so we can depend on those p-values and confidence intervals and standard errors. We're looking for constant standard deviation, normality, and mean zero, and we're looking for identify any influential observations. So we touched on this last week, and I kind of diverted it to this week. So we want to talk about that first. So how do we identify influential observations or outliers? Let me underline that just because something's an outlier or influential as we see does not mean that we should delete it without thinking. We of course want to fix it if we think it's an error, if we can. We can delete it if it's absolutely, like one of these roads, one of these houses has a ton of information in it. It would be a shame to delete an entire observation just because the basement was an outlier. So, we want to delete everything else in the model just because the basement was an outlier. So we want to investigate it first. It might turn out that you want to delete it, but you want to investigate it first. Don't just blindly delete it. So here's what can happen. So I want to see, in a very simple example here, what is leverage, what is studentized residuals, what is Cook's D, and how can we use it? So just checking out this 4 points right here, 1, 2, 3, 4. Check out the check out X, it's not significant. You can check out the parameter estimate, it's pretty close to 0.3. Just adding 1 point, we saw with the movie data, can really change things, right? Those 4 points down there are the same exact 4 points. This guy up here is 1 point, and look at what that 1 point did to it went from 0.3 to 2.06, and the p-value is super significant now. It went from not significant at all, with 1 point, it did a bunch. So let me, shoot. So let's just keep rolling with it. So what is it that it does that? Here are the two things that we're looking at. This is just a way for me to show it. Is with it is the red line, without it is the blue line. So that includes it, and that excludes it. Pretty clear. So okay, so how can we assess this? We can intuitively look at it, and we know, but how can we quantify how big of an outlier that is, whether or not it's enough that we should really look at it? So what is the idea of leverage? So we're going to talk about two things here. One is leverage, one is studentized residuals. Turns out if it has both, that it's going to be very influential. That's really the way things become influential. So there's X1, that's X1 minus X bar. Leverage, I want you to record in your mind forevermore, leverage is a function of the distance each point is from X bar. It has nothing to do with Y. Leverage has nothing to do with the response. It only has to do with the explanatory variables. In this case, there's only one, it's X. So the leverage, it's not only X1 minus X bar, but it's proportional to X1 minus X bar. So the leverage for each point has its own leverage. So the leverage for X1 is a function of X1 minus X bar. X5, you can see, has a much larger leverage. And all the points in between have pretty small leverage. X5 has large leverage. There is the definition of leverage. You can see here that it's a function of Xi minus X bar. The bigger that gets, this is the sum of all the Xi's minus X bars. So the bigger Xi minus X bar gets, the bigger the leverage is. And it's got this little constant here at the end. Cool. So you can see on here that that point that's we agree is super influential has high leverage. Think about it real quick. I usually draw this on the board, but we'll just use it as a thought experiment. Think if I kept this red point on that line. Let's say that I kept it on this line, but I shrunk its leverage. So I took this point and I moved it to right there, to right where my arrow is right now. So I'll keep the arrow slow. So there it is up here. Let's keep it on that red line, keeping the same trend, but let's move it right here. Do you think that if I had just 5 points and the 5th point was right here in the cloud of the other ones, do you think X would be significant at that point? And I encourage you to play around with that if you think it is, because as soon as you shrink that leverage that much, it's going to kill the influence. So X would still have a very high p-value. The farther you bring this in, right? If I kept it along that line, I bring it down here. So the more I include it in these points, the less influential it is. The more I bring it away, the more leverage it has, which we'll find out the more influence it has. So that's the first idea, is leverage. Function of the points X minus the average of all the X's. Has nothing to do with Y. And you can see a plot here. What's that?
Professor, you said it's a function of X, but you're drawing it along the line. Is that just for illustration? Because I would think that X, even though it's on that line, you really mean from left to right, because you said if I move it across, move along the line, but that line is a function of X and Y, you really mean moving the point from left to right for the leverage, right? Or all the way to the left. If negative 30 would have as much influence as positive 30 does, regardless of Y.
I guess you said a lot there. I mean, it matters if this point is here or if it's over here, because we're talking about a function of residual as well. So I just think keep it along this line just as a heuristic measure to say that it's along the same trend. So this is the trend line. So if I just bring this point in, it's still trying to get it to move in that direction, but it's not going to be as influential. It's not going to move the estimate or move the p-value as much as it will when it's over here. If you change this to negative 30, it's not going to have the same exact influence because X bar will change, right? X bar will be it'll be this point, this X plus negative 30.
Got it.
And that'll change the relationship in here. But for now, just the big point, and I think this will make more sense when we look at the residual. For now, just the influence changes increases as the leverage increases. But certainly if you start moving around, it has different effects. And you can see here that the leverage, right, I'm just showing that with this plot, this is subject versus leverage. I forgot to tell you this. When I made this data set, I always forget this every semester, there's actually 2 points on each of these. It looks like 4 points, but there's actually one right on top of it, just to nail it down a little harder. So there's really 9 points up here. So it looks like there's one, but there's another one sitting right on top of it. Doesn't really matter. This shows you all the leverages are down here, but that one has huge leverage up there. So the next thing is studentized residual, where the studentized residual is simply the residual, the actual residual, divided by the standard deviation of the residual. And so the standard deviation of the residual, notice, is, of course, a function of the square root, the RMSE, the square root of the MSE, but it's also a function of the leverage. So, and the leverage is a number between 0 and 1, because it's always positive. The leverage is a number between 0 and 1. So as the leverage gets bigger, right, as this gets closer to 0.9, this thing becomes smaller and the studentized residual becomes bigger. So as the leverage increases, the studentized residual also increases, and obviously it's a function of res I. So I'm going to tell you what residual I really means. I'm going to do that right now. Yes. Residual I is, let me see when I'm going to put it on there. So I'm not quite there yet. Basically, I'll have another plot here for you in a second. The residual is called a leave one out residual. So the residual that we're going to use here is this point minus the estimated value at x equals 30 without that point in the regression, right? Right now, it looks like that residual would be pretty small. Looks like the line almost goes straight through that point. But the residual here is actually big because res I will be the distance between that observation and the predicted value without that observation in the model, which would be way down here. So I'll show you that here in just a second. But notice that the studentized residual of this one is way above 2. It's a standardized residual. Anything above 2 or less than -2 is considered unusual if you have a reasonable amount of data. Darn it, did I not? Yeah, okay. So last thing here, and I'll clear up that one a little more. So far we have leverage and we have the studentized residual. And what we're going to see in this plot is that the Cook's D is a function of the studentized residual and the leverage. We can see it right here. As the studentized residual gets big, so does the Cook's D. As the leverage gets big, so does Cook's D. So when you have big studentized residual, and big leverage, you have high Cook's D, and there's various rules that are actually quite far apart. I like to use a Cook's D bigger than 1 is considered significant. But you really just got to look at it and kind of see relative to the other observations, is it noticeably more significant than others. Really, when we're looking at this, and you'll see a bunch of them in the future, if 1 really stands out and it's bigger than 1, I might go look at it. There's another rule, and this is the rule that SAS uses. If it's bigger, it's a very conservative rule. If it's bigger than 4 over n, then it's significant. So it's the same rule if n is only 4, right? But if n is 100, now you're looking at 0.04. So that's a pretty big difference of a threshold. Some papers say 1, some papers say 4 over n, which obviously for big sample sizes is a very different threshold. So which one do you use? Which one is right? They're both wrong. They're measures of influence, and they're it takes time and money to look at observations if they're errors, and this is just a diagnostic to help you know which one to look at. If you think something's an error and you look at it and it has very little influence, just leave it in the model. It's not going to make a big difference if you take it or take it out. But if you think something is an error and it's got high influence, you might want to spend some money because you're going to get a very different model if you have it in or if you don't have it in. So let's see that in. The Cook's D is a blend of both. So let's look at the Cook's D of that point that we say is so big. There's the residual. That's what we're calling the residual. And there's the leverage. Huge leverage, huge residual. So we look at Cook's D. Notice this is the Cook's D, and it is enormous. 250, so that's well above both. So, and not only is it well above both, but it's well above all of the other ones. So I would definitely go check this one out because as we've seen, the inference is quite different, keeping it in or not. You're not usually going to see something with this bigger Cook's D. It's just for example. To Max's point, you can have points with high leverage and high residual. You can have this point here that has high leverage and low residual. So I'll let you, this is from the book, I'll let you kind of just check these out. So this one has high leverage but low residual. Without the point, it's very little. The difference between with it and without it isn't much, but it still has high leverage. This guy here has high leverage and high residual. Without this point, the line's way up here, and so that residual is really big, and of course it has high leverage. That would have high influence more than likely. This guy here has high residual, but with it and without it, look, the line doesn't change very much because it doesn't have any torque. I like to think of that as torque. It doesn't have any leverage to pull that line around. So it has very low leverage, but it has high residual. But if you take it out, it's not going to make that big a difference. Probably going to have, and you can see Cook's D here, probably going to have low influence, lower influence. So very good plot there. You can see all of them. So I told you that we would do this one day, and today is the day. There's the data set. So I said that some points are right on top of each other. So there's the points. So we've covered these 3 plots here. We're now going to cover these 3 plots here, and we'll leave these for another day. So this one here is the studentized residual plot. Notice it has lines at 2 and -2, and that is the cutoff for usual and unusual. Great. This plot here is probably my favorite plot. It is leverage versus studentized residual. So you can see it's got 6, I'll call them quadrants, but it's not the right term. It's got 6 sections. This section here is low leverage, low residual. This section here is high leverage, low residual. This section here is low leverage, high residual. this little section here that's kind of squeezed out because there's no observations down there is low leverage, high residual, negative. And these two are the special ones. This is high residual, high leverage, and this is high residual, extreme, high or whatever, low residual, but extreme residual and high leverage. So these are the ones you got to worry about. These are the ones that should be influential. And notice we've got a point that's well into that section. It's got very high leverage, very close to 1 leverage, and it's got very high student residual. I mean, like 11. So it's no surprise that Cook C will be very high. So these three here are showing you, are things unusual, in really identifying which observation you should go to hunt down in your data set to see if it's significant or not, or to see if it's an error or not. So great. So was that all I had there? Good. So that is my first part. That's on kind of looking at these plots. You can get this. This is default output from ProcReg. Notice I don't have to do anything to get this plot from ProcReg. If you want to get this plot from ProcGLM, you just have to add plots equals all, and you'll get this plot. You'll want to put a plot like this in your project. Great. We just added another tool. That's what I like about in the first course here, and in the second course, we add tools constantly. So great. So I said the next thing I wanted to look at, I kind of wrote down from all the quizzes what I wanted to look at, is extra sum of squares, adjusted R squared, this reference method, and making confidence intervals. So this guy here is the echolocation data. I'm going to show us an example of the extra sum of squares test. So let me tell you, you've already done an extra sum of squares test, and it was when we did the lack of fit test. So if you remember over the immersion, we had some questions on that lack of fit test, where we compared a simple linear regression model to the separate means model. We used the ANOVA table to compare two models, both of which were not the equal means model. Great. So, so fantastic. In fact, that gives me a point because another question was on the ANOVA table. So, in fact, let's just do this. This is one day where we really need to. Okay, so Simrat, if you're around, I just saw your note, so should be able to get back in. What was I doing? Oh yeah, I'm doing this. I'm going to come back out. Little bitty chart on here. And we'll head on to the next thing. Not really any questions, of course. So these are the things we're going to cover. I'm going to erase this part. Great. So remember our ANOVA table. Oh yeah. Let me just plot this up here. All right. Okay. Remember what we did before. You're going to have to go back to Unit 5 in your head. But before we had maybe 1, 2, 3, 4, and we're going to call those right now classes or levels. And remember we had something that looked like this, and we spent a lot of time talking about it, and it was awesome. Right, we have something look like that. And we said, hey, let's make an ANOVA table out of that. And all we were doing was ANOVAing. We were ANOVAing. We were analyzing the variance, analysis of variance. And how are we doing that? We said, okay, well, let's compare the sum of squared residuals of the equal means model, right? Hopefully that looks familiar. Take this point to there, this point to there, and sum them up, square them for every point up there. That's the equal means model. That was the total. I'm going to put a T there for total. This is an ANOVA table. So just so it looks like an ANOVA table, that's error, that's model, and that was the equal means model, EMM. And that's it right there. So remember, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 observations. N equals 12. Try to remember what the degrees of freedom of that were. Remember that that is one parameter, so it's N minus 1, so that was 11. Awesome. So then we said, okay, I want to compare that. Does it make sense to let each one of these have its own mean? right? That's the separate means model, and that's what we did with the ANOVA. So with the ANOVA here, we said, okay, that's 1, 2, 3, 4. That's the separate means model. And this one was 12 minus 4, which was 8. We subtracted, that became 3. This is the sum of squares. This is the degrees of freedom. That's the mean square. That's the F statistic, and that's the p-value. So just a little review, things we've seen before, but this minus this gives us that. Now the t here, right, that's summing up those squared residuals. I'm just making this up. Let's say that that's 1,000. And I'm just making this up. Now when I do these guys here, let's say that that's 80. That's the sum of squared residuals for the separate means model and the sum of squared residuals for the total model. And of course that would leave us with 920 up here. And this one here would be, in fact, just make life easy. Let's make that 1,100. And let's make that 1,020. I knew I could make it complicated enough to. So I don't want to waste a whole bunch of time here, but anyway, that is 100. I don't even really need that, so I don't know why I did that. But this is 80 divided by 8, that's 10. And that is, just so I don't mess it up, divisible, so that's 340. Just dividing 1020 by 3, 80 by 8, so on and so forth, and we get this, right? So that is 34. And that's a very big, so this divided by that gives me this guy, and that's very extreme. That's an F38 distribution, right? An F38 distribution, and at 34, that's a very, in fact, 34 is like way out here. It's a very, very small p-value. So I reject. What do I reject? I reject that that this would happen by chance. I would reject that just the random scattering of points would give me such a drop in the sum of squared residuals as this big a drop, as 1,020. That wouldn't happen very often. If there was no relationship between the mean and the levels, that wouldn't happen very often. And so we said, okay, we'll reject the null hypothesis that that there is no difference here, that the separate means model. Well, reject the null that the equal means model is a good fit, and side with the separate means model. Okay, so all that was reviewed. The only difference with that ANOVA table that you're looking at now is that it's not talking about the separate means model. It's talking about a different model known as the regression model. So what ends up happening here is, I'll put this one over here. In fact, we don't want to, let's just change this one. The only difference is we're still comparing it to the equal means model, but this is now a regression model. So when you run proc GLM or you run proc reg, this row here is no longer the separate means model, it's the regression model. And I want you to think, how are these numbers going to change? How are the degrees of freedom going to change? You're going to do this in a second, so we'll get really good at it. How many parameters, let's say that's simple linear regression. Y equals theta naught plus theta 1 x. So how many parameters does the simple linear regression model have? You can fire it into the chat room or just yell it out. How many parameters? The separate means model has 4 parameters. What's that? You got it. You say
2.
2, that's right. Beta naught and beta 1. So it's not as good as the separate means model, right? That's what we did with the lack of fit test. We compared these two models with the lack of fit test. So maybe go back and watch that video. But that's what we did. And the ANOVA table that we're talking about in this section, we are just simply comparing the ANOVA model, the regression model to the equal means model. We're just comparing the regression model to the equal means model. So this guy here will be 12 minus 2, which is 10. And this guy here will be 1. And we'll fill all these guys in appropriately. If this here rejects, right, I don't want to come up with, let's say that that's reduced to 100, so that is 1,000. So that's 1,000 divided by 1 is 1,000. That's 100 divided by 10, which is 10. So this F statistic just became 100. 1,000 divided by 10. So the S statistic is 100, yada, yada, yada. That's even way out, even more out here. It looks like the regression model fits better than the equal means model. And that's all the ANOVA table is telling you. Now, when we do the extra sum of squares test, we're going to be comparing, again, just like the lack of fit model, for the extra sum of squares test, we're going to be comparing a reduced model to a full model, a reduced model to the full model. Both of them will not be the equal means model. But notice that the equal means model is the most reduced model you can get. It's in the reduced model zone. We can always think of this as the reduced model. We can always think of this as the full model. And last but not least, we don't have to make this a simple linear regression model anymore. If we want to plot it, to look at it, we do. But let's make this plus beta 2 x2. And you can barely see that. But that says beta naught plus beta 1 x1 plus beta 2 x2. We can't really see it anymore. But I still have sum of squared residuals. I have a predicted value, and I look at the observed minus the predicted, and square it, and I get my residuals. The only difference is that now has 3, right? 1, 2, 3, and it has 3 degrees of freedom. So what's going to change?
9 degrees of freedom.
Yeah.
Right, 9 degrees of freedom? You said 3,
9.
I think you meant 9. Yes.
That's great. That's right. And
And then 2 for the model.
All right. Yeah. And that will change up here to 2. Great. And if we could have 10 explanatory variables, well, actually, that's a good point. We could have 10 explanatory variables, but notice what would happen. Very important point. Let's say that that's beta naught plus beta 1 x1 plus beta 2 x2 all the way to beta 10 x10. Long story short, that's 11 parameters. So we'll only be left with 1 here, right? 12 minus 11 would be 1. That's fine. We'll just have really wide confidence intervals because we won't have a good estimate of the MSE, but we will have an estimate. But notice what happens if I only have 12 observations and I try to fit 11 explanatory variables. Right? Then I've got an intercept, 11 explanatory variables. Now it's 12 minus 12, that'll be a 0, and I can't have any MSE. Right? That'll be a 0. Again, if I have 11 explanatory variables, that'll be beta naught plus 11 beta 1s. That's 12 altogether. 12 minus 12 is 0. That's a very, very, very important point. And
Professor.
so that's, yes.
Could you please explain this 12 minus 12? I mean, I didn't get this part actually. Like,
Okay.
how come it is 12 minus 12?
So if I fit this model, right, I only have 12 observations. So if I try to fit a model that looks like this, right, let's say that I got really overbearing, and there's a lot of data sets out there like this, where you have what's called a lot of explanatory variables and not a lot of sample size. That's called a big P, little n problem. Big P,
Okay.
Lots of parameters, little n, low sample size. So let's even do this one. Well, let's do this one. So this is 11. So this is, if I try to fit this model, this is height, weight, age, shoe size, SAT score, ACT score. You've got all 11 different readings on each person, but you only have observations on 12 people. So notice what that is. That's 1, 2, right? There's 12 parameters here. Beta naught, beta 1, count them all up all the way to beta 11. There's 12 parameters. So n minus p is 12 minus 12. That'll be 0. Does that make sense?
Okay, all right. So if we have less number of records, then this thing will happen, right?
That's right. If you have more, if you have more explanatory variables than you do sample size, this will happen.
Okay, cool. Thank you.
Yeah, no problem. And so this, you'll see in the table, it'll just fill in that as a 0, and it'll put a dot here. And when that happens, right, we can no longer, in our parameter estimate table, everything will go blank. There'll be no standard errors. There'll be some estimates, but there'll be no standard errors. There'll be no t-statistics. There'll be no p-values. So if you ever see that, that's probably what happened. Check your ANOVA table and see if you have an estimate of the MSE. We've gone on almost every week how important that is. because it's involved in every standard error estimate. So if we don't have it, we don't have any standard errors. If we don't have standard errors, we don't have t-statistics. If we don't have t-statistics, we don't have p-value. Cool. All right, so let's get on with it. The more we play around with it, the more we use it, the better we'll be at it. So I'm going to share my screen here. I don't want to, I'm going to just going to go for something over here on the side. See if I have a data set that I can easily, here you go. Here's the BAT data set. Everybody knows this data set, right? We're pretty familiar with this one. So if I do a proc GLM, data equals BATs, and I do model, let's just do model, I know the assumptions are met. I'm just messing with the numbers here. So let's do model energy equals mass. Boom, like that. In fact, this is going to be a problem. Cool. And if I do energy equals mass like that, and then do run, let's think, right? We're going to see how many observations we have. I'll know that in just a second. And then think, this is simple linear regression. Think about what those degrees of freedom should be. So I'm going to run the whole thing here. That's what the ANOVA tells me. The ANOVA table tells me. Let me just say that real quick. Here are all the energies. The equal means model is just the mean of all those energies. If you don't tell me a mass, my best guess is just the average energy. Not a very good guess, but it's my best guess. So the equal means model is just the average of all these energies. Of course, if mass tells me something about energy, then I'll get a better estimate of energy. If you tell me the mass, that'll reduce the residuals, and I'll have a better fitting model. Now I'm curious. Let's see what it is. So I run that guy. There's my plot. Certainly looks like they're correlated. I come up here to my ANOVA model. Looks like there are 20 observations because that's a 19. The equal means model, you can see that here, right? The, where is it? The energy mean. The mean of all 20 of those energies is 19.5. That's the equal means model. In order to estimate that, I burned degree of freedom. So that's 20 minus 1 is 19. Notice that it's a simple linear regression model. 20 minus 2 is 18. And then we start asking, there was 3,000, our sum of squared residuals is huge. After the model, our sum of squared residuals is smaller. We explained a lot because I just subtract those guys. I get my mean squares, right, by dividing. I divide those to get my F value. Holy cow, it's the biggest one we've seen yet, 108. Of course, that's a very small p-value. It looks like the regression model fits better than the equal means model, which per our lack of fit conversation last time, and I encourage you to watch that again or watch it for the first time if you haven't seen it yet, but you'll have a different perspective now. So that's like saying that, hey, I've got this, if you watch that video, it's saying, hey, I've got this soccer player, and he's better than a high school soccer player. And you're like, great, he could be just better than a high school soccer player, or he could be the most amazing player on the planet, because both of those people are greater than this high school soccer player. But if instead you tell me that I've got this soccer player, and he's almost as good as Pele, or I forgot the guy's name already, but as the most amazing soccer player on the planet, Ricardo or something like that. So if you say that he's almost as good as an amazing player, that's telling you way more than if he's better than an average player. So that's the same thing here, is that right now I'm just telling you that this model is better than the equal means model. Whoop-de-doo, at least we have that. But so anyway, that's what this is telling you. But yes, indeed, the sum of squared residuals drops more than you would see by chance. So you prefer the regression model over the equal means model. Okay, so where do we want to go with that? Got a little long-winded on that. Stop sharing. Nope, not stop sharing. Okay. So let's get on with how to do this. So, okay, great. Actually, this is perfect because that's the data set we just looked at. So what if now, though, I want to compare two models. One is a subset of the other one. It's called a hierarchical model. So one is a subset of the other one. You can imagine that the subset one is the reduced model, and the full model is the full model. So let's say that we have this. Everybody's familiar with this one. This is with mass. After accounting for mass, we have the categorical variables, and we have all the interactions. This is the full model. You can't have any more parameters in this model than this with those variables. So that's the full model. Maybe what we want to do is see if the interaction terms should be in the model. What we can do is test for both of them at the same time, simultaneously. Not look at each individual parameter estimate, look at them all together. And, this is just two of them. We could test, if we have bigger full models, we could test a whole bunch of them at the same time. But we're just going to test both of these beta 4 and beta 5 at the same time. How are we going to do that? That's our null and alternative hypothesis. Should the interaction be in it? That's the alternative, or should it be out of it? That's the null. So we're going to do this with an extra sum of squares test. So here we go. So there's our full model. And so the full model, we want to know what is its degrees of freedom and how well does it work. I don't care about this one. That's comparing it to the equal means model. I don't care about that at all right now. I'm just running this ANOVA to get the sum of squares here. So how well did it do? What was its sum of squares? That's an important number. And what was its degrees of freedom? Great. So now we're going to look at the reduced model. Notice this model doesn't have beta 4 and beta 5. We're going to look at the difference. What was its sum of squares? Watch this. Ba-bam! You might argue that's pretty close, right? It's less. The sum of squares residuals is smaller here, but of course it's smaller because it had more. It's probably explaining some noise. But the whole point is, let's not speculate on it. Let's run the test. So this is smaller than this. So was it worth adding those extra two parameters? Was it worth adding an interaction? Again, I'm running these ANOVAs, but I don't care about anything on here except for this degrees of freedom and this sum of squares. And this degrees of freedom and this sum of squares, because I'm going to build my own ANOVA with it. So there they are. There's the full model. There's the reduced. And here is my, here is my ANOVA model. So notice this is the full. Well, let's go to the reduced first. That's the reduced model. So that's 16 and 0.55. That's 16 and 0.55. Fantastic. That's 14 and 0.504. That's how I compare two models. I put the reduced model down here. I put the full model up here. And to a question from the quiz, I know the distribution of the ratio of the mean squares. I know that distribution. If I start messing around with the degrees of freedom, I don't know that distribution anymore. So the question was, why do I look at the R squared instead of the adjusted R squared when I'm doing an ANOVA? And that's because the adjusted R squared will start messing with these degrees of freedom and messing with that ratio. And then I won't know the F distribution. My whole point here is I know that this statistic has an F214 distribution. That's a particular shape. And so I can get my p-value from that. So here's the reduced model. Here's the full. All you're going to do is put those in, and the rest is clockwork. 16 minus 14 is 2. 0.55 minus 0.550 will just be this 0.0485. Divide horizontally. Divide horizontally, get these two. Divide vertically, get your F. And we've done that a million times. This one fails to reject. That was not a big enough drop. That was not a significant drop. There's not a lot of evidence here that an interaction is necessary because it doesn't explain a significant amount of the variance in the energy. Awesome. So what did I want to do here? So this was the conclusion. So we refit it. Notice without the interactions. We refit it without the interactions, and we get these guys. And it looks like the adjustments. Looks like the adjustments to the intercept aren't very significant either. It looks like all these are about the same line, given the data that I had here. So the data are consistent with the hypothesis of equal median in-flight energy expenditures between echolocating bats and non-echolocating bats after accounting for the bat's mass, for the p-value of 0.730. We're just interpreting this estimate. So, okay, fantastic. Conclusion, there's not sufficient evidence to suggest the lines are not parallel. That's what an interaction does, right? It allows you for non-parallel lines. We rejected that, or we failed to reject the null hypothesis that they are parallel. Okay, so that being said, what I'd like you to do is, you're doing pretty well, take about 3 or 4 minutes and try to, I want you to, on your paper, if you could, draw a ANOVA table, just like this. Draw an ANOVA table, and you may not get through this, but draw an ANOVA table and fill it in. Fill it in as best you can. At least try to get the degrees of freedom and the sum of squares right. At least try to get the degrees of freedom and these sum of squares, because you can get those directly from the screen in front of you. So I'll go ahead and read it. What we're trying to do is, here's our full model. Assume we have randomly sampled 35 students, n equals 35, and the sum of squared residual error for the fit of the model above, the full model, was 84.67. That's the sum of squared residuals. It's the sum of squared. We also fit a model without the last three terms, without beta 7, beta 6, and beta 5. We also fit that reduced model, and the sum of squares increased to 130.7. Find an F statistic to test if the slopes are the same for the four classifications of high school students, right? These are when I'm testing beta 7, beta 6, and beta 5 are the interaction terms of the categorical with the continuous variable. Those are the terms from last week that allow us to have different slopes. So I want you to test simultaneously to start the test to see simultaneously if we should include those three, if we should include the possibility of different slopes, or if there's not enough evidence that we should suggest that the slopes are not parallel. So take a second and see if you can fill out that ANOVA table. I'll give us about, and it's totally fine, I just want to give us a little example. I'll give us about one more minute. Nothing else would be good practice just drawing the ANOVA table. Sometimes that helps. Okay, great. Totally fine, and we want to learn from it. So I'm going to give you the answer. Let's just go ahead and look at it. So there it is. So we know that we had, I'm going to go back real quick. We had 35 students, right? We have 35 of these guys. And so assume we have randomly sampled 35 students and their sum of squared residuals for the model above was 84.67. We also fit a model without the last three terms and found the sum of squares to be 130. So without these, you have beta naught 1, 2, 3, 4, 5. You have beta naught and beta 1, 2, 3, 4. That's 5 parameters. So this guy here is 35 minus 5, which is 30. Of course, with those three, you have 3 more parameters, so that's 8 parameters. So 35 minus 8 is 27. So that's where the 27 came from. Fill in the sum of squares. At this point, once you have these 4, it's easy. You just subtract up, divide sideways, divide top down, get your F, get your p-value. Any questions on that? That was a big step. That's what an extra sum of squares test is. No questions? I'm moving quick. Slow me down. I'll slow me down. Okay, I can't see anybody, so I'll assume that we're good. Again, practice that. I think I was going to say I think you'll see it in the homework, but you won't see it in the homework. So make sure, but you might see it on the final. So beware. In fact, you'll probably see something like that on the final. You'll definitely have to build your own ANOVA on the final. It might be a lack of fit test. It might be this extra sum of squares test. But in one way or the other, you're going to have to build your own ANOVA. Okay, great. So now we have a lot of questions on this R squared. So fantastic. Let's go for it. We're switching gears. We're going to climb that mountain, see a nice scenic overview, grab a little water, and now we're going to keep climbing. So here is the idea. R squared, we're very familiar with R squared. It's just the sum of squared, the amount of the sum of squares from the model divided by the total sum of squares. It's how much variance, what percent of the variance total did we explain? And we can see that the total It's a squared residual, and so that's why we're seeing these squares here. The farther away the point is, the more it adds to the sum of squared residuals. That's an important thing to see. So if you're 4 away, you're adding 4 squared, 16. Right? Let's just say you're 1 away. If you're 1 away, that's 1 squared of 1. You're adding 1 to the sum of squared residuals. If you're 2 away, which is 1 more than we were before, 2 squared is 4. So if you're 1 away, you're adding 1. If you're 2 away, you're adding 4 to the sum of squared residuals. And that gets exponentially larger, of course. So, so we're looking at the sum of squared residuals. Farther residuals make a big play in the lack of fit, is basically what we're saying. But that's what we're looking at, is the R squared. We know that as we add explanatory variables to the model, because we can do that now. With multiple linear regression, we can keep adding beyond one explanatory variable. In fact, I don't know if we know that yet. What you're going to find out is that as you add explanatory variables, no matter what, R squared will increase. Dramatic pause. Doesn't matter if it's explaining trend or noise. If you add explanatory variables, R squared will increase no matter what. In fact, depending on how you add them, you can get R squared to be 1. Because what we might end up doing is stop explaining trend and start explaining noise. And when we start doing that, that's what's called overfit. So here's a quick example. R squared can always be made to be 1 or 100% by adding explanatory variables. Consider this model. Consider y equals beta naught plus beta 1x. Looks like I'm probably explaining trend there. And if I use this model on another data set where I don't know, for a future data set to make predictions, it's probably going to be a pretty good model because I'm fitting the same trend. What exists in the future should be the same trend as now. That's the assumption anyway. R squared is 0.638. However, if I fit this model, which is just a polynomial, it's based on the same explanatory variable, but with these interactions, x squared, x cubed, x fourth, x fifth, look at what I get. Right? This is just math. This is just algebra, pre-calculus. That is the line that I get. What is the R squared on that? What is the sum of squared residuals? That line goes through every point. Each residual is 0. The sum of squared residuals is 0. So it explains all the variance. But do I think that that's an amazing model? Do I think that that model is going to give me the best predictions? And the answer is no, because if next time you see a 4, you guess this value, it's not, right? The idea is that we're assuming if we assume this is the trend, remember we're assuming a normal distribution at, say, y equals 4. We're assuming the normal distribution of y's at r equals 4. That means from draw to draw, it's going to be a little bit away from this line, either above it or below it. The line is just the predicted mean of that distribution. If I make 100 draws, I'll have 100 blue dots right here at 4, and they'll all be a little bit above and a little bit below, and a lot of them will be really close. But they're not going to be just sitting right on top of each other. So somebody with an R squared of 1 says, oh, well, at 4, it's going to be a 12. Well, it's not going to be a 12. It's not going to fit as well. In fact, if this is the reality right here, if it really is a normal distribution with a mean at like a little more than 8 when x is 4, this is going to overestimate it most of the time, right? This looks like a pretty big overestimate. So if I keep guessing 12 when x is 4, I'm going to overestimate what happens in reality. We don't want to do that. So an R squared of 1 does not mean that it's an amazing model. It might mean that it's what's called overfit. So this is a new data set. So I'm showing here is, hey, now I just sampled from the same distribution. I sampled from the same population. And if I use the model from before, it's going to predict trend. The R squared should be about the same. It's not going to be exactly the same because of noise, because the same pattern, the same exact values don't repeat themselves because there's standard deviation. There's some error in there. But if on that data set, on this new data set here, if I use this line to do the prediction, look what will happen. I'm going to say that those are the predictions, and my residuals are going to be much bigger. And so that R squared actually turns out to be much smaller, that actual R squared, the sum of squared residuals using the red line.
Quick question, Professor.
Yes.
So if we have this overfitting and our R square is close to 100, how do we know which explanatory variable we need to take out and to make it best fit?
So that's what we're about to cover. So how do you know which one?
Like, is there any parameter or like some kind of a matrix we need to follow?
Basically, what you're going to do is, let's go here. I don't look at it from this point of view. So if you have this huge model that you think overfitting, first you're going to get rid of variables that are insignificant. So if we actually fit this model, most of these beta 2s, beta 3s, beta 4s are not significantly different from 0. They have very high p-values. So first of all, we get rid of those. And that should bring it down. Second of all, you're going to keep doing that in an iterative fashion, watching the adjusted R-squared. The adjusted R-squared accounts for the number of parameters you have in your model. So let me wait till I get to an example, because this was a tough example to explain it to. But how do you determine which ones to take out of the model? Number one, you're going to look at the p-values and subtract them that way, take them out that way. Number two, you can actually do an extra sum of squares test and test a bunch of them at the same time. Number three, you're going to build your model not from the top down. I guess that's a backwards elimination, but you can build it from the ground up. So just keep adding variables and keep adding significant variables. And you can do what's called the stepwise regression that you'll learn next week, where you add a variable and then check to see if it made another variable insignificant. So long story short, there's a lot of methods to do that. One of them is by looking at this adjusted R-squared. And you hit on a question that we're going to actually have addressed in a lot of units. But I guess that's where I'm at right now. I'll show you a quick example here that should help you answer that question as well.
Okay, thank you.
Cool. Yeah, I'll have to table that one for a moment. It's a partial answer. So adjusted R-squared, it's adjusted. The R-squared is still a function of R-squared, but it's adjusted. And you saw from the videos that it's a function of both the sample size and the number of parameters. So P here, and you always have to see how it's parameterized. P is the number of R-squared penalized. P is the number of explanatory variables without the intercept. So that -1 is including the intercept. So R-squared adjusted is computed using this formula, where K is the number of predictors. So you don't have K up here. I need to fix that. For P is the number of predictors. So here's an example. On those plots that I showed you that come out of ProcReg and ProcGLM, you can find the adjusted R-squared in ProcReg in the normal tables. You can find it in ProcGLM from this plot. You can see adjusted R-squared. They kind of hide it in here, but you can get it from ProcGLM there. So that is, given that data set, that is that. Now, if I fit this model, question, I've got R-squared and adjusted R-squared there. So watch what happens to R-squared. The R-squared becomes 1. I can't even plot it. Actually, I'll plot it here in a second for you. I'm using a different method. But so for this one, notice that the adjusted R-squared is 1. Notice for this one, kind of answering your question, if I start subtracting off beta 5, notice that the R-squared goes down to 0.8924. So of course, I just subtracted out something and it doesn't fit perfectly anymore. So the R-squared is down to 0.8924. And now, since I have notice with the R-squared is 1, the R-squared is 1. Well, I guess if the parameters are 6, then you'll have n minus 6. We only had 6 observations. So you don't have an adjusted R-squared here because you're dividing by 0. But here we're not. We got 0.4632. And notice that adjusted R-squared is bigger than this adjusted R-squared, which suggests that this model right here, is actually more appropriate than the simple linear regression model. And clearly, it's trying to fit some curve. It's suggesting, the data is suggesting some curve. Of course, we only have 7 observations. But that's what it's saying. Anytime the adjusted R-squared is there to compare models. In the quiz, I got a question of what is the interpretation of the adjusted R-squared? And there really is no interpretation. R-squared has a great interpretation. The amount of variance, the percentage of variance in Y that's explained by the model. it really should say it's the percentage of variance in the sampled y, and the y's in the sample that's explained by the model. Because it's misconceived, it's misunderstood that R squared is explaining the population variance, or else that would be a great model. So it's explaining the variance in the sample of y that's explained by the model, the relationship between x and y. So, but adjusted R squared is just there to compare two models. So I'm comparing this model to that model. This model wins in terms of adjusted R squared. And you can calculate the adjusted R squared for this model by doing that. And for this by doing that. What's that? Oh, we're good. So cool. So, again, if you do plot equals all in ProcGLM, it'll give you the adjusted R squared here. So you can always get the adjusted R squared. I'm actually going to show you ProcGLM select next week, and you'll be able to get the adjusted R squared very easily from there. So back to that echolocation problem. So let's check it out.
Professor, I have a question.
Yes, please.
So having an R squared of 1 is not good because you're overestimating everything, and it wouldn't be good representation of the population. But it seems that you compare models with the adjusted R squared. So would having an adjusted R squared of close to 1 be good?
Sure.
Like on the slide you're on right now.
Yes, let's see. Yeah, so having an adjusted R squared close to 1 is more telling than having an R squared. It's way more telling. There's way more evidence that you have a decent model than the R squared. But you could still have, you can still be overfitting and have a high adjusted R squared. It'll be tougher though. So, to answer your question, we're going to have to look at other diagnostics. There's other statistics such as likelihood statistics such as the AIC and the BIC and the SBC that we'll study in great detail next semester. Maybe I'll introduce them this semester. But to answer your question, yes, you'd like to have your adjusted R squared close to 1. And usually that's not as much evidence for overfitting as an R squared of 1. An R squared of 1 is, an R squared of 0.99 is probably a very high evidence that you're not fitting trend anymore, that you're actually fitting noise. But again, that depends on what you're measuring, what your X's and Y's are. You know, if there's a natural phenomenon that's relating X to Y, if X actually is causing Y, then you will have a very high R squared in adjusted R squared. But yeah, Joshua, that's adjusted R squared close to 1 is possible and is favorable. Sure.
Cool, thanks.
Cool. So let's check it out. Back to the VAT echolocation problem. We got our full model, and we see in our full model that, right, remember that we did the extra sum of squares test on this, and we said that these two are not needed, right? That this beta 4 L mass, the beta 4 and beta 5 are superfluous or redundant, or not very useful. But notice the adjusted R squared is 0.9771, and it's got a high R squared. So if we look at the reduced model here, we've got that the adjusted R squared without them is actually a little bit higher. But so that's why we have multiple tests to look at things. You don't want to just base it on the adjusted R squared, but the adjusted R squared is suggesting that you don't need those terms. The extra sum of squares test is suggesting you don't need those terms. And to another question, which is always comes up, is this idea of parsimony or Occam's razor, is if you're trying to decide between these two models, and you're like, if you're just deciding on the adjusted R squared, there's really not much difference between those two adjusted R squares. There's really not much difference between those R squares. And in all things being equal, you usually prefer a smaller a model with less terms in it. And the reason why that is especially, I say you usually prefer that if your object, if your question of interest is interpretation. Because the more terms in these interactions that you have in the model, the more you have to qualify it. And if it's not necessary, then you'd rather just say, hey, after accounting for mass, or just in this case, not even after accounting for mass, just saying, hey, the for every one additional unit increase in log mass, or I guess in this case it's a log-log model, so for every doubling of mass, the ratio of the medians of energy increases by a factor of 2 to the beta 1. Unfortunately, it's a log-log model, so we have to do all the interpretation. But that's much easier than saying, if you're a bird, then it's this. If you're a bat, then it's this. If you're a non-echolocating bat, then it's this. You have to qualify everything. And in this model, it's just saying, hey, they're all related the same. And there's no reason, given this data, there's no reason to believe that it's not. So what that means.
So if the R-square and adjusted R-square for both the model is approximately same, so does the F value plays any role in that? Because F value is a significant difference in these two models.
Sorry, I got the part that said adjusted R squared microphones. I just moved it, so maybe this will be better.
Okay. I was saying that, I mean, adjusted R square and R square in both the models, they're approximately similar, very close to each other, right? But if we look at the parametric estimation table, the F value has a significant difference between the two models. So does this F value plays any role in selection, which is a better model, or no?
The only part I missed was the F value or a different value?
Yeah, the F value. Right, because adjusted value is same. Right. So does this play any role when the other values are same?
Yeah. So I think what let me just say this. You said I believe that the F value changed significantly, and I think we're just subjectively saying that because it went from 163 to 283. I think if you looked at the P values, you might. I mean, that's just because we think that those numbers are bigger. The difference between a 163 and a 283, they're both saying that what we would see, remember those are just comparing it to the equal means model. Those are just saying that these models really beat the equal means model, that you would never see this by chance. Very, very small possibility that you would see this kind by chance. So we're going to suggest that some of these betas are not equal to 0. I get what you're saying is that it looks like the F value is big, but really in the F distribution, there's not a big difference in P values from 283 to 163. There's a much bigger difference in the F514 and F316. Notice these are different distributions as well, right? This is a F514. This is an F316. This isn't a real significant difference in F values, I guess is what I'm saying. And we saw that in the
Okay.
Cool.
Okay, cool. Thank you.
Cool. And, well, we'll just leave it at that for there. So practice problem, calculate. I'll leave this one because we're running out of time, but I encourage you to go back just to traditionally in classes, hey, take some time and try to find the adjusted R squared. But you've got the R squared, and we have the formula, so you're just going to plug it in and see that you get exactly that. And it's a good, warm feeling when it all works out. It's math. That's why I love being a math major, because you always had those. You either had the moment where you didn't get it right and it was disappointing, but you keep working at it and you get the exact right answer. There are black and white, right, wrong answers in math. As you've seen in statistics, there's some fuzzy subjective room for interpretation there that we just get used to. So here is the problem. What did I want to do here? So this is just another practice problem looking at the adjusted R squared. That is a tuna. I bet you didn't expect that. So what is the last thing that I wanted to do here? We covered we covered the extra sum of squares test. We covered adjusted R squared. What we didn't cover is these. So I guess we won't cover that. I was going to cover the reference method. You guys know how to set the reference variable. And I guess I'll let that come up as we come by. The last thing I guess I wanted to do, unless, is there anything I didn't cover that somebody wanted to see? I'll just go through an example here at the end. If not, is there anything that I didn't cover yet? Yes.
Well, I do have a question on that practice problem that you gave before when we did the ANOVA table. Yeah, where you get the 35 students. I'm going to assume that the error model is the full model, and basically what you did was you took 35 students and you subtracted out the 8 parameters to get to 27. And then since you said you did a fit without the last 3 parameters, that's the reduced model, so that goes into the total on the bottom row. They get added in. Then 84 and 67, you know, the bigger numbers goes on the bottom, you subtract it out, and then from there you worked your way over.
Maybe. What I did to make this, and it would be good for me to animate this, in fact, too, do this really fast. This is what I did. Check this out. Oops. Oh, that didn't work. Anyway, first I did the total. So the first thing I did is I came over here and I said, hey, the reduced model is this model. The reduced model has 130 sum of squared residuals, and it's got the last, without the last 3 terms. That's the reduced model. We could write it, but that reduced model looks like this. That's the reduced model. 1, 2, 3, 4, 5 parameters. So that's 35 minus 5 is 30, and that is the sum of squared residuals for it. So, so I come over here and filled in 30. 35 minus 5 is 30, and I filled in the sum of squared residuals. That's the reduced model.
Yep.
That's the reduced model. This guy up here is the full model. So that's the next thing I went after. I said, hey, I can fill that in too. The full model has 1, 2, 3, 4, 5, 6, 7, 8 parameters. 35 minus 8 is 27. The associated sum of squares is 84. It reduced. Did it reduce enough? So I filled in 27, and I filled in the 84, and that just came from the problem.
And then everything else is derivable.
Exactly. And then every time I go 30 minus 27 is 3, 130 minus 84 is 46. So I've got this one. After I have that, I start going horizontally.
46 divided by 3 is 15.
That's right. Just divided by that.
84 divided by 27, 15 divided by 13.14 is 4.89 is your F value, and then figure out your P from there. With 327.
What's that?
Thank you.
Yeah.
I said yes, with 327 on the F distribution using 4.89 to get your P value.
That's right. Great. Okay. The last thing that we'll do here is just, I'll take us through one more example that I pulled out here. And then I got to set up for that next class. I do need to put more than 30 minutes between these things, but let's rock. So here is an example that's kind of got everything this whole semester in. This is the alcohol metabolism example. So, shoot, it takes a long time just to explain this. Basically, we had 18 women and 14 men, and I'll just give you the top level of it. There's 18 women and 14 men, and when they wanted to see if there's a couple of questions of interest, but basically, if women metabolized alcohol differently than men, if they metabolized alcohol differently than men. And so they took 18 women and 14 men, and they gave some of them, or for each of them, they gave them an IV with ethanol in it, which is alcohol. They gave them an IV, which bypassed their stomach. And then they actually had them drink the same amount. And then they recorded how much alcohol was in their blood afterwards. So the first pass metabolism is how much alcohol is left in your system after your stomach and the enzymes in it have taken the alcohol out. So the theory is, maybe that men have more enzymes and they can drink more and they're not as drunk after they drink the same amount. That's one hypothesis. Another hypothesis might be alcoholics. You hear sometimes alcoholics, well, they're training themselves to drink, so they don't really it takes them a whole bottle to get drunk because their body is processing it faster because it's used to it. So we're going to test some of those. So one question is, several questions rise. Do levels of first-pass metabolism differ between men and women? Is there an alcoholism effect? And can the difference be explained by postulating that men have more enzyme activity in their stomachs? So dehydrogenase activity is the enzyme. So if you look at the data, here's the data. We have the subject, 1 to 32. Some of them, we'll look at this one here. Well, let's just go. Metabolism is the response. So our metabolism is how much we metabolized, how much of the original alcohol was metabolized. Gastric activity is the enzyme. That's an explanatory variable. The gastric activity is how much enzyme is in the stomach. Clearly male and female, 1 for female, 0 for male. That's just a gender, and 1, 0 alcohol. So these are both dummy variables describing a categorical variable. And let's answer some questions. So do levels of first-pass metabolism, does metabolism differ between men and women? That's our first question. And in that question, we're going to do this. Steps in multiple regression. First, we're going to plot the data. There it is. So we plot it. This has got a little bit of everything. Loving it. So we plot the data, and we see that we might have 2 leverage points out here, right? Those might be very influential. We'll have to see. And it looks like they are both, we've got the coding down here, male non-alcoholics. Those are both male non-alcoholics. So, great. So let's see. This is metabolism again, and that's our continuous variable, and the codings are the codings of the 4 different possibilities of male alcoholic, female alcoholic, male non-alcoholic, and female non-alcoholic. There we go. See, we have some linear trend. Looks pretty good. So steps in multiple. We plotted the data. Now we want to develop some tentative models. And we're going to use the questions of interest, account for confounders, and maybe add any relationships if we need to. So several questions of interest arise. Number 1, do levels of first-pass metabolism differ just between men and women? Notice there's no gastric activity in there. So we know how to do that. We've got this model, beta naught plus beta 1 gender. Notice there's no continuous variable in there. This just becomes a 2-sample t-test or a rank sum test if you want it. Question number 2 is there an alcoholism effect? And so these are the models that we want to build for these. So question 1, that's a model that we can use to address question 1. This is the model that we can use to address question 2 by putting the alcohol effect in there. So this is saying, I guess we don't even really need the gastric effect in here for this, but can the differences be explained by postulating that men have more dehydrogenase activity in their stomachs than women? Oh, that's why I put these together. So we're going to use this model to address the second 2 questions, because I want to know is an alcoholism effect affecting question 3 as well. So this model is going to answer question 1. This model is going to answer question 2. So I've developed my 2 tentative models. So do first-pass metabolism differ between men and women? I can just run a ho-hum. I can run the test here, or I can run a rank sum test. Here I just ran the test. Notice I look at the female effect. The female effect is significant. So yes, it does look like there's a significant difference in mean metabolism between men and women. Now, why is the question? Right? We've established that there is a difference in mean metabolism of alcohol between men and women. Looks like men have a higher metabolism. But why is that? We'll proceed with a non-parametric test. I think I did that. Here's the non-parametric test. Remember back in the day, the rank sum test. And the rank sum test also rejects at the 0.004. So we say here that the median metabolism of males is significantly greater than the median metabolism of females. So that's all this says down here. But again, why is that? Maybe this gastric activity has something to do with it. Is it the fact that it's just they're males, or is it a fact that males happen to have higher gastric activity, and that's why their metabolism is better, or metabolism is greater? So let's check it out. Of course, we want to ask this: is there an alcoholism effect? Why I'm doing that one in the beginning, but we'll answer that one here. So we want to fit the models. So I fit the model. Notice here I'm saying model metabolism equals gastric intersection sex, which is the gender, intersection alcoholic. I don't know if I've shown you this yet, but this pipe, I think I did last time. Pipe says fit gastric by itself, sex by itself, alcoholic categorical variable by itself. Also fit gastric interact with sex, gastric interact with alcohol, and sex interact with alcohol, and gastric interact with sex and alcohol. That gives you every possible combination. So that was that full model. Notice this full model here. This one, this is that model. It's gastric by itself, gender by itself, alcohol by itself, gender and alcohol interaction, gender and gastric interaction, alcohol and gastric interaction, and all 3 of them interaction. I think we had that question last time, and so there's an example of it. Great, so we fit the models, there it is, and there is the parameter estimate table. Now you might ask, why don't we just look at this every time and it looks like that the three-way interaction is not significant, that this one's not significant, that one's not significant, this one's not significant, and all of those are the alcohol ones, and they're all not significant. And in this case, since they all came back insignificant, you'd be right. But you could just look at this. We're going to get the same answer when we do the extra sum of squares test, right? It doesn't look like there's an alcoholism effect. But what could easily happen is these could all be close to 0.05, and this one might be 0.04. And remember multiple comparisons. We're actually running a bunch of correlated tests here, and we're not making any multiple comparisons, even though we're running all of these tests. Every time you see a p-value, it's another hypothesis test. So what we prefer to do, instead of if these are really close, is we'll test them all at the same time to see if there's any significant evidence of an alcoholism effect. And that's the plot you see, but that's what we're going to do next. So this is it doing the model. Notice there's really no evidence. These are all pretty high p-values of an interaction effect. But what I'm going to do here in a minute is do a extra sum of squares test. But anyhow, I'm going to keep going this route. I forgot what my next slides are. So we'll just keep going the model route. We're going to evaluate the residuals. We just fit a model. How good are those p-values? So we look at them, and we say, oh, well, it looks like there's some evidence of increasing standard deviation, which would inflate my MSE, right? It looks like these residuals are bigger than what I would expect them to be under my assumption, which would make sigma squared hat bigger, which would make those standard errors bigger, which may inflate my p-values, may give me bigger p-values. And notice I've got some influential observations per Cook's D over here, and I've got one that's in the super zone. I'm not really worried about these other ones, but I am worried about that one. So I'm looking at those guys. So I say, okay, well, let's look at those guys. Let's investigate some influential points. Notice that these are by observation. Those are 31 and 32 out there, and we can go track this one down. But I'm most worried about this guy here, and I see that you can use this code to get these individual scatter plots and label them by subject, so that's how we can see it. This is the leverage versus the residual. There it is right there. That really dangerous one is 31, right? That guy right there is observation 31. Decently high leverage and very high residual. Okay, great. So there they are. I'm looking at those guys. I'm looking at those guys. 31, 23, and 32. Well, notice 31 and 32 are these ones that we noticed in the first place. So how can we handle that? We don't really want to delete data if we don't have to, but in this case, in some cases, it might help. What we're going to do is just chop them off. And what we're going to do, and you can do this in your project, you can delete observations. But when we do that, we narrow the generalizability of our model. This model is no longer good for gastric activity greater than 3. And that's fine. We just built a model. Our model now is generalizable, if this is a random sample, to all males and females in this population with gastric activity less than 3. We don't have a model for anything greater than 3 because we chopped them away. So we still have a good model. We just have to preface it with the fact that it's only good piecewise for gastric activity between male or female between 0 and 3. So we chop those away. Reduce the range of inference for gastric to 0 to 3. And that's fine. You can definitely do that. You just have to write that in your report. So then we get rid of that. We get rid of that effect. So we get rid of those. So I just took the data and deleted them. That's in SAS how you can do it. Or you can just do it in Excel and re-import it. And we refit it. And notice we still have no alcoholic effect, and those p-values have even gone up. And we like our residuals. So we look at our residual plots now. They're never going to be perfect, but they're pretty darn good. And yes, we still may have, we can go investigate this point further if we want. I didn't keep going with that, but repeat as necessary. So, okay. So I think I don't remember looking at that. So it looks like I did go and investigate this a little further. But I don't think I took it any further than that. I don't think I deleted them. So those are the ones that you would look at in the future. Oh, I know what I'm saying here. The reason why I'm not looking at them is because we said that one with high Cook's D was 1 and 20-something. So 1 and 20-something. 1 is only because it's high leverage, right? It's not high residual. So I'm not really worried about that one. It's just high leverage. 23 is just high. It's not high residual, right? The residual is very small. It's just high leverage. I'm not really worried about those two because they're not both. And this guy is high residual but not high leverage. So I'm not really worried about them. I personally not really worried about them unless they're high leverage and high residual, unless for any case, you know, the wording of the problem or whatever situation I'm in warrants it. But otherwise, I'm not worried about those because they're not both. So you can read that part, but we'll just keep moving. We're almost done. So we evaluated the residuals. We looked at, and now we're going to answer the questions of interest. So we identified any influential observations. We took care of them. We narrowed the scope of our model. Now let's interpret the coefficients and make predictions. Is there an alcoholism effect? So we already looked at it through the parameter estimates, but this is how we could do it with an extra sum of squares test, and it's a very good use of it. Notice that the alcohol is combined in beta 3, beta 4, beta 6, and beta 7. All of those have an alcohol effect in it. So I'm going to test all 4 of those at the same time. So there's my null and alternative hypothesis. All beta 3, 4, 6, and 7 all have alcohol in it. Let's test those all at the same time. And so we simply run a ANOVA model for each, not because I care about anything else except for that degrees of freedom and that sum of squares, and that degrees of freedom and that sum of squares. Take a look at that for a second and make sure that makes sense. This is the reduced model. It's in the bottom row, 26, 20.22. This is the full model. It's in the middle row, 22 and 19.4. Subtract, divide, divide, and you're good. Notice almost no evidence of an alcohol effect. Great. So we're going to use that model. That's our final model there. Beta naught plus beta 1 gastric plus beta 2 gender plus beta 5 allow different slopes for gender. Maybe gastric is related to metabolism differently for men and women. And that's going to be part of our last question. So the data are consistent with no alcoholism effect for those gastric levels between 0 and 3. Note that we're conditional on 0 to 3 here. We've qualified our model. So can the difference be explained by postulating that men have more dehydrogenase activity in their stomachs? We agreed there's a difference in means and medians between metabolism for men and women. Can that be explained by a different relationship between gastric activity between men and women? So we're going to look at that gender gastric variable. So this is a little extra piece that doesn't help you see the immediate big picture here, but it's a little thing along the way. Notice that I've gotten rid of the intercept. And this is something you can do if it makes sense. It's your subjective ability. But we've got somewhat low sample size here. If we believe that it makes sense that the regression lines should both go through 0, then why fit an intercept? Just force it to go through 0. When gastric activity is 0, force metabolism to be 0. And I'm not a scientist, but it stands to reason that if somebody has no enzymes in their stomach and you put alcohol in there, what goes in is going to come out because the enzymes didn't take anything away. Of course, the assumption is the enzymes are the only thing that work on the alcohol. But if that's the assumption, then going through the origin, which is 0 gastric, 0 metabolism, makes sense for men and women. How do you do that? Right here. You can put in no int. And that's going to save you a degree of freedom. Right? Now I only have 2 parameters, 1, 2, because I'm not fitting an intercept. And notice when we do that, the gastric, it does suggest that the slope of that men's line is different than the slope of the women's line. Amazing that for increased gastric activity, the men metabolize. For whether you're a man or a woman, the rate at which you metabolize alcohol is different based on your gastric level, right? For 1 unit increase in gastric level, you get a different return of metabolism if you're a man than if you're a woman because the slopes are bigger. So the idea here is this is the last piece, but this is the end of it. The data suggests for those with gastric activity between 0 and 3, we've qualified that the change in metabolism rate for women for a 1 unit increase in gastric enzyme is 0.87323 units less than that of men. We've got our evidence in there. In other words, the mean first pass metabolism for males, and we don't have enough time to go through this assumption here, but I guess we'll try. Notice that this is beta 1 divided by beta 1 plus beta 5. Beta 1 is the gastric activity for men. I'm sorry, beta 1 is the gastric activity for women. Because remember, gastric gender was 0 for men and 1 for women. Gender was 0 for women and 0 for men and 1 for women. 0M, 1F. So when I put a 0 in here, beta 1 is the slope, is the gastric activity for men. So that's it right there. For males, you got it right there. For males, it's 0. So that gastric, 1.59 is the slope of that line. For women, the gastric activity is beta 1 plus beta 5. Notice beta 5 here is negative. So the slope of this line is 1.598 minus 0.87. So that's what I have here. Beta 1 divided by, so beta 1 is 1.599, divided by 1.599 minus 0.8732. That's dividing the gastric slope of men divided by the gastric slope of women. It looks like it's estimated to be 2.2 times that of females. Men are, for the same gastric level, men are metabolizing twice as fast. Assuming that men have more gastric activity in their stomachs than women, this increased slope per unit activity provides an explanation for the increased mean first pass metabolism of alcohol. So you're looking at it right here. For the same gastric activity, by the time we get out to 2, this would explain why men have a higher mean gastric activity than women. And as we increase gastric activity, that difference becomes greater. And it's because men process, the evidence is suggesting men have a metabolism and metabolize more alcohol per unit gastric activity more than women. So how do I say that? That the relationship, for every 1 unit increase in gastric activity, men increase more metabolism than women, or the metabolism rate of men is greater than women. So you can check this out, but that is a full explanation. I had a request for a real-world example. I try to make all these examples somewhat real-world, but this is a lot. I mean, it's got extra sum of squares test. It's got no intercepts. It's got how to look at the plots. It's got how to look at the residuals, how to handle influential observations, so on and so forth. So thanks for sticking around. I have to run, but I want to make sure there's no questions before I go. Is there any questions? Is there anybody in here, first of all? It's always good to come
Still
back.
here.
All right. I think I have a quick question.
Yes.
So on your slide 28 of your PowerPoint over there where you do the SAS code, and you say that for the output, you make a data set and you assign values to the student residuals and the CLIX-D. Where is that generated from in SAS? Does it just have these whenever you do a proc reg?
All right. Sorry, Joshua. Is this the slide?
Oh, my 28 is different than yours.
Where is it? What does it look like?
It's titled Influence. It has a plot of studentized residual versus leverage. I think you have a more updated PowerPoint than mine.
Oh. Did you see it as I was going through it?
It's before question 1.
Is it in the alcohol
Like
example?
4 slides before question 1. Up.
Before question 1 of the alcohol?
Yes.
Let me know when you see it.
Oh, there. Oh, no.
Here's the one that you have. This is a separate one. So slide 28. Slide 28 is the tuna on this one.
I guess we have a. I don't know. I got it on Canvas before the class started, but if it's fine, I'll just explain what the slide has on it.
Can you share your screen, Joshua?
You saw it in my presentation?
No, I don't think I saw it in your presentation.
Oh, okay. Well, that's probably why then. So, I wonder which one I put out there.
It just says Unit 13 live session is the title
Joshua,
of the PowerPoint file.
Joshua, can you share your screen?
I'm gonna have to run, but I think I got it right here. Is this one slide 28?
Yep. There we go.
Out?
Right there at the bottom left, or output out equals T. So you make a new data set or something with T, and it gets all these student residuals and cooks D and leverage and everything. Where are those coming from?
Down here?
Yes.
Those are being calculated from staff. So this is it's a good thing to see. Go ahead.
So whenever you do a proc reg or anything in SAS, you can output what all the leverage is and the cooks D is for all that.
If you want to do a detailed
the
analysis,
variables for later, yeah.
if you want to do a detailed analysis like this, then yeah, you have to output them and then do your own plotting on it, just like this. And you can ask for T out. Just says, hey, make a data set called out. Student is a reserve word. The variable in that data set will be called res. Cook D is a reserve word. I called it the same thing. H is a reserved word. H means leverage, so I just called it LEV. And P is the reserved thing. It says, hey, put all the predictions and put it into Y hat. And then
is
over
there a
here,
list of all the reserved words somewhere?
yeah, if you search proc reg, on the internet, the SAS proc reg, then go down to the output statement, and you'll see all of them, all the things.
Oh, cool.
Output. Yeah.
Oh, okay,
cool.
Yeah, thanks.
Yeah, no problem. I'd take you out there, but I got to set up the classroom for the next one. But that's, but yeah, if you go to
paste it in chat there.
In fact, if you just go to Google and proc reg SAS output, and it'll take you right to where it will show you where all these things are. So,
Yeah, put the link in the chat.
Awesome.
Professor
So,
Sadler, last question for today. So what's the plan on the homework? I mean, you said it's a group work and all.
Oh, poop. Looks like, so I didn't get your, so let's do this. I will put out an Excel sheet tomorrow, because my plan was just to divide everybody up that's on the screen right now. But I'll just make that more organized. Tomorrow, everybody tonight, this will be better anyway, try to look, your homework for tonight or tomorrow, before I put them out there, will be to look at this data set and look at the project on your own. So just get acquainted with the variables, get acquainted with the project description, try to understand it on your own. Tomorrow in the afternoon, I'll put out the group, the groupings, the group membership. Then email your group, and then you'll already be familiar with the problem, ask each other, and you can start from there, and then I'll see you on Sunday. So I will put it out there tomorrow, groups, and it'll be, so check those out. I'll make a quick announcement tomorrow. It'll be probably between 12 and 2 Central.
Okay, thank you.
Thank you for reminding me. Yeah, I meant to do that. So, but check out those resources. Maybe check out Kaggle, and look at that video too. Please look at that video before tomorrow, and that'll really kind of make you prepared to talk with your partner. So that's it. Sorry, I got to run. I think from now on I'll put an hour between classes, but I'm sure you guys are done anyway. You probably don't want any more time. Awesome. Happy Thursday. Great job. Are you ready for the second to last whammo to get out of here? Awesome. John, take us out.
All right. Quick